Okay, so hello everybody. Today we have John Jasper who will tell us about new strongly regular graphs from real line packings.
Thank you so much for having me. I'm really happy to be here. Excited to tell you about some recent research I've done on real line packings and strongly regular graphs. So the outline of this talk, it's pretty simple. My goal in most of my research is to find vectors in space, either real or complex. Most of this will be real. Real vector spaces, find vectors that are maximally spread out. We'll talk more about what that means, but in particular, these optimizers of spread outness, they sometimes have very, very nice representations. And from these representations, we can often deduce the existence of some graphs, strongly regular graphs. So some new strongly regular graphs are going to come out of all of this. So we need to start with, what do we mean by spread out? And so the notion of spread outness that we use most of the time is the notion of coherence. And so just a little intro to what the heck does coherence mean. So we're looking at the maximum inner product between any two vectors, and we have unit vectors here. And so really we're looking at the cosine of the angle between the vectors, and we want to look at the smallest angle between any two vectors. And so you can see in the picture that the coherence of these guys is the cosine of that angle, theta. But something's a little bit more complicated here because there's that absolute value sitting in the way there. That absolute value is doing something a little bit different, which is, so illustrate this with another example. Consider the following vectors, not too different, but now look at the angles between them. Well, the smallest angle between any pair of these vectors is obviously the one that I've labeled theta, but is that the coherence? Well, it turns out that it's not the coherence, because of that absolute value, is instead of measuring the smallest angle or the cosine of the smallest angle between any two vectors, it's measuring the cosine of the smallest angle between any two lines spanned by those vectors. So our notion of spread outness is really a notion of spread outness of lines. And the vectors that we're picking are just representations of those lines. We're just grabbing a unit vector in each one of those lines. So in this case, that turns out to be the smallest angle between any two of the lines spanned by these, and hence that's the coherence of this collection of vectors. Okay. So the point here is that we're trying to minimize the coherence, but that's the same thing as maximizing the minimum angle between any pair of the lines spanned by these vectors. Okay. And so when we're working on measuring how spread out vectors are, we're trying to spread them out as much as possible. In fact, we're trying to spread out the lines spanned by these vectors as much as possible. And so to put that succinctly, our goal in a lot of my research is, given a dimension and a number of vectors, d and n, find a collection of vectors, n of them, in Rd, such that that coherence is as small as possible. So if I'm trying to minimize a quantity, generally when I want to minimize something, I'd like a lower bound. Because then if I say, well, it's equal to that lower bound, then I know I've minimized it. And so the lower bound that we use really commonly is the Welch bound, which says if you have a bunch of unit vectors in Rd, of n of them, then that coherence number can never be any smaller than this horrible looking square root monstrosity. But luckily, it gives us a fixed number that we can sort of shoot for. We want that to be our coherence. If we can get that coherence, then we know that we have minimal coherence, because any collection of unit vectors will have coherence bigger than or equal to this. And in fact, when you meet that bound, you get a nice equivalent condition that's sort of more linear algebraic, which is when we have equality in this bound, so when we know we have a minimizer of coherence according to this bound, we can say that that's the same thing as saying the following two properties hold for our vectors. The first one is called tightness. So a collection of vectors is called tight if they satisfy this sort of modified Parseval equality. So in some sense, the vectors act very much like orthonormal basis, except there's this A here, whereas if this were an orthonormal basis, then of course this would just be 1. So that's tightness. And then the other condition is that the vectors need to be equiangular, Well, really, we mean the lines spanned by the vectors are equiangular. That is to say that the absolute value of the modulus of the inner product of any two distinct vectors should be the same for any pair of distinct vectors. If we have both of these things, then we'll call it an equiangular tight frame, and that's the same thing as achieving equality in the Welsh bound. And so we're on the hunt for these ETFs because they're things that we know for certain will solve our optimization problem. They'll minimize that coherence. So in this talk, we're going to look at ETFs from a few different angles. And one important way to view ETFs is not just the individual vectors in the ETF, but actually through the gram matrix of the ETF. So a little bit of notation on this slide. First of all, when I talk about ETFs, when I talk about n vectors in d-dimensional space, I'm going to always write them as a matrix that is d by n. So the columns of that matrix are my vectors that I'm concerned with. So the gram matrix is this matrix down here. So that's just phi transpose phi. It's just the matrix of all the inner products of all my vectors. So when I have a collection of n vectors in Rd like this, I'm going to assume that they span the space so that this matrix has rank D and that each is unit norm. Then I can rephrase those two conditions of equiangularity and tightness in terms of this gram matrix. It turns out that tightness is equivalent to saying that, well, that gram matrix, if you square it, you get a multiple of itself. So that gram matrix is a multiple of a orthogonal projection. And then second, we can say, well, all those inner products, that we can write those just as dot products because we're just in Rn. All those inner products, if I normalize by B, then they're all one, which is to say that all of so to rephrase these in terms of the gram matrix, first, I need to have ones down the diagonal. That's the norm one condition. Tightness is just saying that matrix is proportional to a projection. It's a scalar multiple of a projection, a non-zero positive scalar multiple of projection. And then that just says that the off-diagonal entries of this gram matrix have constant modulus. So when we can find a gram matrix with these properties, it turns out that we can go backwards, and I'll say a little bit more about that in a minute. But what this slide is just emphasizing is that if we're looking for these ETFs, then we can kind of just compute the gram matrix and then just look at it and say, does it have these three properties? If it does, it's an ETF, and we've found this object that we're searching for, this optimizer of coherence. Okay, so let's look at a few examples of ETFs so that we don't have, sort of no examples in our bank. I don't know, do people ever chime in during these talks? Okay, you unmuted, so I'm going to pick on you. Can you give me an example of an ETF? What's a trivial example of an ETF?
Something like an identity matrix, no?
Yeah, an identity matrix, or really any orthonormal basis. So you'd have an orthonormal basis up here, right? Then all the inner products are zero between distinct vectors, so it's equiangular, and it's tight because, well, its gram matrix is the identity, so it's a scalar multiple of projection. Yeah. So there's a more complicated example. In fact, any unitary matrix, that'll be an example of an ETF. So these columns. But that's not the example I care about here because orthonormal bases always exist, right? In any dimension, I can find a real orthonormal basis. But there's a slightly more non-trivial example, which is I take a unitary matrix like this, or a scalar multiple of a unitary. And what I do is I delete the first row because it's a row of all ones. And what's left I end up with is an equiangular tight frame. Why? Because the columns used to be orthogonal, so now all the columns have inner products -1. And if you compute the gram matrix of this thing, you'll see that it just has all -1s on the off diagonal, all 2s down the diagonal. So it's a scalar multiple of a projection. So you can just directly check that this thing is an equiangular tight frame. It's equivalent to say the rows of this matrix are orthogonal and all have the same norm. This is a good time to point out that when I do this, I don't always normalize my columns. I sometimes let them be norm 2 or norm squared 2 or norm squared 3 because it makes the numbers a lot nicer. Otherwise, I have a lot of square roots floating around, and that's just a matter of scaling. So really what I'm looking for here, as with this example, is the Gram matrix has all of the entries on the off diagonal are all constant modulus, and all the diagonal entries are the same. That turns out to be one of these examples that we saw early on, which we sometimes call the Mercedes-Benz frame. And that's sort of this first slightly non-trivial example of an equiangular type frame. We can do this anytime we have a unitary matrix where one of the rows is the all ones row. We can simply remove that one row, and the resulting thing is always an equiangular type frame. In fact, this always gives us an equiangular type frame with n+1 vectors in Rn. Right? We don't have to use this Hadamard matrix. It didn't matter that the rest of the rows were all plus minus ones. We could have just had any unitary with the all ones row at the top. Delete that, and you've got an equiangular type frame. Turns out this one is the tetrahedron, or the vertices of the tetrahedron. So I want to get a little bit more non-trivial, and I want to look at the following example, because we're going to play with this example quite a lot, and it's got a few things I want to point out. So this example, the thing at the bottom, which if you look at it here, it has 16 vectors in 6-dimensional space, okay? The way that we obtain this thing is from these smaller pieces. So right here, this is a R by R+1 ETF. It's the one we created on the last slide with all these plus minus. So we just took that 4 by 4 Hadamard matrix and deleted the all ones row. And then this guy here, I don't want to focus too much on it, but it's a nice block design. It's a nice combinatorial object. So it's a Steiner system, and the key property is that this Steiner system needs to have R ones per column, where this one has R rows total. So when we do this, so what we can do is we can take these two guys and we can do this operation that we sometimes refer to as the star product, because it's kind of tensor-like, but it's not quite a tensor. And so we didn't know what to call it, so we informally call it the star product. And then the resulting thing here is this thing called a Steiner ETF. This was actually discovered by Goethals and Seidel back in 1970, and then rediscovered by a few of my co-authors, and they generalized it to the complex case. The nice thing is that this gives us a truly non-trivial example of an ETF, 6 vectors or 16 vectors in 6-dimensional space. And it's really not that bad to prove that it's an ETF. In fact, I'll compute its Gram matrix for you in just a moment. But you might be wondering, how the heck would you come up with such a weird operation in order to find an ETF? Well, the answer is kind of interesting, and it'll come back in a while. The answer to how you might discover such an interesting construction of an ETF really starts with a different object. So the discovery is it starts with this object called a McFarland difference set. So what's a difference set? A difference set is it's a nice subset of a group. So here my group is Z2 cross Z2 cross Z2 cross Z2. And then I'm taking this subset of that group. What I look at then is I look at the difference table, which I've written down here. The difference table is just all of the differences, so row minus column. And what I observe is that all of the entries in this guy all of the entries from all of the elements of this group occur in this table, well, in this case, exactly once. But what we need is for them to occur the same number of times, except for down the diagonal, of course, you're going to get all zeros. So the zero, that's where 0 appears, and it appears some other number of times. But everything else here appears exactly one time. And the reason that difference sets play a role in this is because there's a construction of ETFs that comes from difference sets that I'm going to show you, but I'm not going to explain exactly why it works, because that's the subject of a whole different talk. But the point is that if I then take those particular group elements and I'm going to use them to build an ETF, and here's the way I'm going to use them. So what I'm going to do is I'm going to take the character table of that group, that full group, Z2 cross Z2 cross Z2 cross Z2. And all I'm going to do is I'm going to grab those rows that correspond to the difference set. And it turns out that when you're a difference set, if I grab those rows and extract them from the character table or the discrete Fourier transform over that group, if you want, lots of ways to describe that matrix, this thing here turns out to be an ETF. And the part that I'm totally not justifying is why that difference set property has anything to do with this being an ETF. But like I said, that's the subject of a whole different talk, and it would take us too far afield for now. So you're just going to have to press believe on that. But the observation that you can make here is that that looks, like, okay, I believe it's an ETF, sure. So it's got, all the columns are equal norm. Yeah, that's believable. Their inner products are all the same. In this case, they're all plus or minus 2. All the inner products between distinct columns. And then the rows are orthogonal and equal norm. That's what it means to be an equiangular tight frame. Well, the observation that we can make is that if we were to reorganize these rows and columns in a really special way, then we see that a little bit more structure starts to pop out. And you might not see it there, but if you sort of rip it apart a little bit, then you can see, oh, in these little 2x4s, I'm getting this sort of repeating pattern, right? And so what that tells me is that, well, I might be able to, I don't know, rotate this thing to get a lot nicer representation of it. And so what I'm going to do is I'm going to multiply on the left by this unitary, and what I end up with is that Steiner ETF that we started with. And so what you can do is you can sort of start with this known construction of a difference set and then play around with it a little bit, just rotate it in space, literally, and you end up with this thing here. And it turns out that this, you can generalize in a lot of ways that this difference set construction up here doesn't generalize, okay? So one way to construct ETFs is to rip rows out of a character table, and the resulting rows will form an ETF. I'm here to not talk so much about how to build ETFs, but how to take ETFs and build graphs from them. I needed to tell you a little bit about how to construct ETFs, so you believed me that there were some out there, but I want to talk about graphs. So let's go back to that example, and we can just all press believe on this is an ETF, okay? And in fact, I'll compute the Gram matrix for you. There's the Gram matrix. So I compute the Gram matrix of this ETF, and the only thing that's not apparent is that this thing is tight. That is, that this matrix, this big square 16 by 16 matrix, is a scalar multiple of a projection. But not hard to check, especially if you have this matrix in MATLAB. So this is a graph theory seminar. I'm sure everybody is just staring at that and saying, yeah, there's obviously a graph there. So I'm going to build the graph in a second. But first, I want you to observe that I started with the 6 by 16 ETF. I started with this guy up here, and then it's very easy to build the Gram matrix, right? And you can start to see, hey, okay, I get how you would build a graph from this. But I want you to observe something else first, which is if I was just handed that Gram matrix, how would I build the phi? How would I build that short fat matrix that is whose columns literally form my ETF? Because that's the object I really want. And the answer is, well, it's a nice linear algebra question. It's a nice exercise for like an undergraduate linear algebra class. Given this matrix, how would you build a short fat matrix phi such that this is the Gram matrix of phi? And the answer is, well, there's not a single answer. There's many. This is only determined up to a unitary, right? And so if you go in and you ask MATLAB to produce one for you, you're going to get something like that, which is not nice at all, right? So when we start with a nice representation, we can build a really nice Gram matrix. Of course, the Gram matrix is nice. It's only got 3 numbers in it. But when we start with the Gram matrix, the representation, that short fat thing, that's hard to come by. So in some sense, that short fat thing seems like it contains a bit more information than the Gram matrix. And that's the information that we're going to exploit in order to build new graphs. So let's build some graphs. Okay, so we take phi, we build its Gram matrix, this guy here, and then we're going to do, okay, I don't know this is the most obvious thing, but at least it's the second most obvious thing to do. It's to build the graph like this. Replace all the minus ones with ones, replace all the zeros, replace all the plus ones with zeros, and then zero out that diagonal. Okay. So I build that graph, and then I say, is this a nice graph? I expect it should be, because it came from a really nice, rare, like optimizer type object. And indeed, it's a very nice graph. This graph has three really nice properties. First is that every vertex is adjacent to 9 other vertices. So that every row here has 9 ones in it. And then it has these 2 extra properties. So the first one is it's regular, and then the second 2 are it's super regular or strongly regular. So its adjacent vertices have 4 common neighbors, and non-adjacent vertices have 6 common neighbors. And you say, oh, great. So ETF, build the Gram matrix, build the graph, we're done. But here's the problem. I started out with an ETF. Why couldn't I have started out with one where I just simply negate one of the entries? Let's pick one. How about that one? So if I were to negate that, observe what happens to this thing when I perform the same graph construction. I build the Gram matrix and then build the graph. Well, when I negate, you see what happens to that one column and row is that all the zeros and ones flip. And so the problem is that if I had started with this guy instead, the resulting graph isn't even regular, let alone strongly regular. And in general, I'm not going to just be handed a nice graph that just happens to have this extra property, right? When I'm handed, a nice ETF that happens to have this extra property. When I'm handed an ETF, the columns might be signed up in all kinds of different ways. And so I really am worried that I'm not going to ever get even a regular graph except by a sort of miracle like what just happened, right? So let's explore, how can we build in that extra structure? What can we do to get that extra structure that I'm looking for, that regularity? So first, just to put it up, because it's the subject of this talk, we should say a strongly regular graph is just a simple graph on n vertices. Every vertex has k neighbors, adjacent vertices have lambda common neighbors, non-adjacent vertices have mu common neighbors, and such a thing we call an SRG nk lambda mu. Equivalently, the 0,1 adjacency matrix of G has to satisfy the following relation that I put here in red, where J is the all ones matrix and I is the identity matrix. And the thing that I want to really point out on this slide is that we saw that we can take the Gram matrix of an ETF and build a graph from it, right? And in fact, we were only doing an affine transformation, essentially, to our Gram matrix. And we already know that our Gram matrix of our ETF satisfies a nice quadratic relation. So it's not too surprising that it should, in some cases, give us this nice sort of quadratic-looking relation on that adjacency matrix G. But what we saw on the previous slide was that we're really concerned that the graph we get is even regular. In particular, we're concerned with this matrix. Does it have the same number of ones in each row? Well, if it did, it turns out that's enough to guarantee that the resulting graph is strongly regular. So really, all we have to check for is regularity. And we can phrase that nicely in terms of the ETF. So suppose we have an ETF now, and this ETF has one of the following 2 conditions, which is equivalent to having this. So the first one is the all ones vector is in the kernel of phi. So remember, my phi is built up of columns, and the columns are my vectors. And what I'm saying is if I add up all of my vectors, I add them all together, I'm going to get the 0 vector. That's what this condition says about phi. Equivalently, you could just say that the all ones vector is in the kernel of the Gram matrix by transpose phi. So in particular, it's an eigenvector of that Gram matrix. But another way to go is if the all ones vector is in the row space of phi, turns out that's equivalent to saying that the all ones vector is an eigenvector of the Gram matrix with a non-zero eigenvalue. And the nice thing is I can check that by just saying, hey, what does it mean to be in the row space? It means a linear combination of the rows adds up to the all ones vector. So what I can do is I can just say, well, can I just observe that in my ETF, in my short fat matrix, my D by N matrix, can I just observe that some linear combination of the rows is equal to the all ones vector? If so, then the associated graph that we built 2 slides ago will automatically be strongly regular. So if either one of these conditions holds, then the resulting graph is strongly regular. And it turns out that anytime you build that graph by simply taking the Gram matrix and replacing the ones and minus ones with zeros and ones and zeroing out the diagonal, the only way that can be strongly regular is if one of these two things happens. So let's see it happen. So the nice thing is the example we've been playing with, we can observe it in both ways. So first observe that if we multiply all of the columns by the appropriate signs so that all of these first 2 rows have all pluses instead of the plus minus pattern that we saw before, then, well, the sum of the first 2 rows is the all ones vector. So the all ones vector is in the row space. If you then build the graph as we did 2 slides ago, then you'll end up with a strongly regular graph with these parameters, 16, 5, 0, 2. We can also sign it up. Well, in fact, this is the one we started with because we observed that that thing was already strongly regular before we started, because the way that we just happened to have built it with this star product type construction was it automatically had the property that all of the columns, if you add them all up, you get the 0 vector. So 1 is in the kernel of this matrix. And so when we build the graph, we get the SRG 16, 9, 4, 6. So what this tells us is that we are on the hunt for, we want nice ETF representation because that gives us new SRGs. What's nice? I want to sign the columns in such a way that I can see one of these 2 properties holds. Either all the columns, when I add them together, I get 0, or the all ones vector is in the row space. So anytime I have this nice short fat representation with one of those 2 properties, I have an SRG. I need new SRGs. So I want to verify that they're new. And so how do I do that? Well, I think that we all do the same thing, which is we go to Brouwer's table, because he knows everything about strongly regular graphs, or at least compared to me, he knows everything about strongly regular graphs. And so you're looking for your favorite strongly regular graph. If you come in here and you see the parameters are 81, 32, 13, 12, that row is green. So it's already known that that graph exists, or a graph with those parameters exists. If you were looking for 81, 40, 13, 26, it is known that no such graph can exist. And then most interestingly, there's all these yellow rows that say, hey, for these parameters, there could be one, there might not be. It's an open question. So our goal in this talk is to turn yellow into green. So let's see a prototype, an example from a result from a few years back. There's the construction of ETFs that's very similar to these Steiner ETFs that we've been playing with. It's just a bit more widgety. I just sort of throw a bunch of stuff together. And the nice thing is that you can pretty easily verify all the claims that I'm going to make, but I'm going to leave that as an exercise to the reader. But the construction, it proceeds kind of similar to our Steiner ETFs, which is first we do a legit star product, just like we did before. And it turns out that's already an ETF, but it's not a new one. And so I do a new thing. So I then just add on a big 0 matrix, and then below I add on this tensor product, because it turns out this tensor product guarantees that the resulting thing is the first several columns, right? All these columns here are still equiangular, but they're no longer tight. So I got to fix the tightness. And so I go and I add that matrix in, and that fixes the tightness. Now everything's tight, but they're no longer equiangular because the angles over here between these vectors and over here between these ones are not the same. And then the miracle that occurs is that when I add one more row, that fixes everything. So, like I said, you're going to have to think about this or read the paper, but it's another construction that comes from a pretty natural place. but in its sort of like ripped apart form, it just looks like I'm just throwing stuff at the wall. And I really, really like, I still have that feeling, even though I'm one of the inventors of this construction. The ingredients you need here are a Steiner triple system, which is awesome because I understand everything about Steiner triple systems. Well, at least when they exist and when they're resolvable. I need a Hadamard matrix and I need a second Hadamard matrix, but it turns out this second Hadamard matrix is always twice the size of this one. And so I really only need this one because I can just tensor up and get the bigger one. So the construction, if you put it all together just to visualize it, there it is. You can see it has 7 numbers in the matrix. It's a nice short fat representation. And so the question is, can I sign this guy up? Can I multiply its columns by some signs to get one of those 2 properties? The all ones vector is in the row space, or all the columns add to 0. And currently it does neither of those things. So this construction gave us a bunch of new ETFs, okay? In fact, anytime you have a Hadamard matrix of a particular size, you can build an ETF of this size. And it gave us a new infinite family of ETFs that's closely related to the Spence difference set, if you're familiar with that. But we're concerned with signing these things up. So it turns out that one that we just looked at, we weren't very successful with, but the next larger one we were very successful with. So here's the next larger one. So again, we've got this Steiner triple system, star producted. So we throw in this tensor-like fashion, we add the rows of a Hadamard in there. We put down here a bunch of these little, just this tensor of I with a bunch of square root of 2s. And then there's another Hadamard matrix appropriately scaled and the final row of a Hadamard appropriately scaled. So we were wondering, can we sign this guy up in such a way? And the answer was, well, this one it's a little hard to see, but the reason we went up to this size was because there was a nice Steiner triple system available to us, which is a resolvable one. This resolvable Steiner triple system, we can look at these first 5 rows of the resulting guy. And you can see that they almost, well, they have disjoint support. So if I added them up, well, I would get something that was all plus minus 1s. Right? And then I've got this last row down here that is all just, I guess it's root 3 over 2s, but I don't care. I just need the all 1s vector in the row space. So what I'll do is I'll multiply each column by the appropriate thing so that all those first 5 rows are all positive. And then add the first 5 rows plus a multiple of that very final row, and that's the all 1s rows, the all 1s vector is in the row space. And so what this tells me is if I then build the graph that comes from this, well, then I get a strongly regular graph. It only works for some of the cases. So when H is congruent to 2, if there's an H by H Hadamard matrix, then we get a strongly regular graph on these vertices. And so we were curious, hey, does this give us a new strongly regular graph? So we went to the table and we said, well, I think when I pick H is equal to 20, I get an 820, 429, 228, 220 as my parameters here. And I know it's a funny way to spell Jasper, but it's written right there. That's my name. So we had success with this technique even when we first started. But we were curious, like, hey, can we do any better here? Can we get more from this Tremaine construction? And we were totally stymied. We could not figure out a way to sign it so that the all 1s vector was in the row space in the other cases that we missed, or sign it so that all of the rows would add to 0. But I had an idea a little while back, which gave us some new results. So my idea was, I want to make these vectors sum to 0. I want to sign the columns of this matrix so that the vectors sum to 0, because that won't give me a new strongly regular graph. But maybe the trick that I learned from doing that, I can apply to this whole family of ETFs, and then I'll get some new strongly regular graphs. So I went to the table and I did this reverse engineering thing, and I said, hey, in the table, observe that there's this row here is what would result if I was able to sign that ETF that we just looked at so that the columns all add up to 0, right? In particular, so this is the graph that would result, but I just don't know how to build it. I don't know how to build the ETF that would give me that graph. But I do know how to build that graph because I've studied polar graphs a little bit, and that's a very nice graph. And so I thought, I wonder if I can find a nice short fat representation of that guy that generalizes. So I went to Sage and I said, give me that SRG, because they're all programmed, or a lot of them are programmed up in Sage. And then I built the Gram matrix, which is an easy thing to do. I just have to add the appropriate amount of the identity after I convert all the zeros and ones to plus minus one. But then I have that problem that I mentioned early on, which is I really want that short fat representation because that's where I'm making my money. That's where I'm finding these new strongly regular graphs, is by analyzing the short fat representation. And when I ask MATLAB, it gives me, well, there's the heat map of the thing that it gave me as the 15 by 36 real ETF whose Gram matrix is listed there. And it's kind of nasty. I don't think I can do much with that. But I thought to myself, I wonder if I can clean this up. So I grabbed this horrible, horrible thing that MATLAB gave me. And I said, let's start rotating it. Let's just rotate it around in space and see if we can get it to look a lot more like the ETFs we've been seeing. So I rotated it, and all of a sudden, a lot of structure starts popping out. And I rotated it again and again and again. And after a few hours of playing, I finally realized, oh, there it is. In fact, it looks a lot like the things we've been playing with. It looks very, very similar. It's just signed in a weird way. And I thought, oh, I haven't changed. This thing has the property that all the columns add to zero. Well, so what's the trick here? And if you analyze this a little bit, you can see that you can detect what the trick is. And the trick was there's somehow an all ones row that had to exist over here somewhere, and you have to make it cancel with one of these. I don't want to get into the nuts and bolts of how this proof works. There's a paper about this, but the point is that what doing this taught me is the trick. The trick we could not, with my friends, when we originally wrote the paper about Tremaine ETFs, this type of ETF, we couldn't figure out how to do this. But just by sort of reverse engineering from the graph, it taught me, oh, that's the trick. That's how you sign it up, right? And so the nice thing is that, well, so the all ones vector is in the kernel. Hey, this works for all real Tremaine ETFs. So all of this infinite family that I was able to build with my friends, I can apply this technique, and I get this theorem. It says anytime you have a real Tremaine ETF, you can sign the columns in such a way that they add to zero. And so I was like, well, what's the first instance where this would what's the first instance where I see yellow on the table? Hey, look, there it is. 820, 420, 210, 220. That's coming from H equals 20 in this theorem. And indeed, there was no known construction before. This is the one that we were able to construct before, but this guy was unknown. So we end up with at least a sort of certifiably new construction of strongly regular graphs that we believe is a new infinite family. We can repeat this success. There's another construction that's very similar. Again, it's very related to Svensk difference sets, but I'm running out of time to give any explanation as to why this works, but there's a whole paper about this that we learned. We learned a technique by just basically analyzing Davis and Jedwab's difference sets, and they taught us that, in fact, group divisible designs or what we learned from studying that was group divisible designs can do a lot of the job that Steiner systems have been doing for us up till now. And so what we can do is there's another family of ETFs, in fact, many infinite families of ETFs that are constructed in the following way. We take a certain ETF and tensor it with an identity. And then we take a mystery object here that kind of looks like a Steiner triple system or a Steiner system or a Bibid or something, some sort of block design. And then we do this tensor type thing with a Hadamard matrix, with the rows of a Hadamard. Turns out that that has to be a particular type of group divisible design. This one in particular, actually, this is, when you write it out, this is the ETF. It's another 15 by 36. But the nice thing is, this one has a feature that the other 15 by 36 didn't have, which is, hey, look, these last three rows, if you add them up, they'll be just plus minus ones. So if I sign that thing correctly, if I sign the columns correctly, then the last 3 rows all add up to just being constant. And so that observation gave us the other ones that we weren't able to find before that have the all ones vector in the row space. So the all ones vectors in the row space of all these guys. And so now anytime we have a Hadamard, which is where H is congruent to 1 mod 3, we get a strongly regular graph with these parameters, go back to the table, see that, oh yeah, that one that we were able to find before, but was already known, the sort of the other flavor, the flavor with the all ones vector in the row space was unknown. But now we have a construction of that graph. So we have at least 2 new infinite families that aren't even on the table yet, aren't even listed as known, but we can go even further. And so the place I want to finish here is with some really recent work where we found a new way to construct ETFs that actually kind of almost unifies a lot of the stuff that we've been doing so far and gives us a bunch of really interesting new strongly regular graphs. So this is a daunting looking slide, but I want to remind you that the way that we built that 6x16 that we played with so much, that little red, white, and blue guy that we've seen so many times, was by taking the rows out of a character table corresponding to a difference set. We're going to do the same thing here. It's just that now the group is Z2 cross Z2 cross Z3 cross Z3, and so the character table has 6 roots of unity in it, and so I've color coded it. So hopefully you can at least follow some of the gist of this. But the idea was do what we did before and take the rows corresponding to a difference set. In this case, this really is this Spence difference set, if you like. Take those rows out of the character table, and then we're going to just play around with this a little bit. We're going to reorganize the rows and the columns until we see something that looks, well, at least those first 6 rows look a lot nicer. We can see there's a lot of structure there in those first 6 rows. And all we did was rearrange rows and rearrange columns, no signing whatsoever. And then what we're going to do is we're just going to split this thing up into pieces. It might look like these pieces kind of look bad, but if you observe here, this is omega squared, omega to the 5th, omega squared, omega to the 5th. That's a 6th root of unity. So this is plus omega squared, negative omega squared, plus omega squared, negative omega squared. And then this is literally plus 1, minus 1, plus 1, minus 1. This whole thing is just plus minus the whole way across. Similarly, this is plus minus minus the whole way across. And this one is plus minus plus the whole way across. And so we can do a thing that we colloquially call ripping it apart and just break it down into these smaller pieces. And it turns out that this piece over here is not important to us. This piece can be replaced with anything that any Hadamard we want, even a complex Hadamard if you don't care about getting complex ETFs. These 3 things are doing, or 4 things, excuse me, are doing the work. They're doing all that special work for us. So these guys are what we're going to come to call compatible orthobiangular tight frames. So tight frame, they're tight frames, just like we've been talking about. So orthogonal equal norm rows, if you like, or their gram matrices are projections, or any number of other equivalent conditions. So that's one. What makes them compatible? Sorry, what makes them orthobiangular? Orthobiangular is this neat feature that they're not equiangular, but they only have 2 angles, which is they're either, any 2 columns are either orthogonal, or their inner product has absolute value 1, right? So there's 2 angles, and one of them is 0. So orthobiangular. So these are orthobiangular tight frames, and I've just written their gram matrices right here for you. But the feature that you might not be able to see from this is that if you give me any 2 columns here, there will be precisely one of these 4 guys, which is not orthogonal. So if you give me the first and the second column, it looks like from this I can tell, yep, these 2 are not orthogonal, but these 2 are, and these 2 are, and these 2 are. Another way to say that is if I take those gram matrices and I add them up, there's no overlaps, and I hit everything. So this is a lot of what the compatibility is more than this, but that's a lot of what we call compatible. So compatible orthobiangular tight frames. These four are an example of that. And in general, oh, I'm sorry, there's a tech problem here. So in general, we have the following theorem. It says if you have a list of L orthobiangular tight frames, so this is orthobiangular and tight, that they have this extra two properties. The first one is the one I mentioned, which is the Gram matrices. They're off-diagonal supports. They all partition. They'll partition all the off-diagonal entries. And the last thing is just some integrality conditions that make sure that all the norms line up correctly. You saw that one of these in this last example here, one of these was a different size than the others, right? That's part of compatibility, is one has to be a different size than the others. They all have to be the same size, but there's a little bit more to that. It's complicated and not very illuminating, but that's why I just swept it under the rug and called it compatibility condition. But anytime that happens, if you simply take the rows of a Hadamard matrix and tensor them one by one and build that big matrix, just like where we got it, that's always going to be an ETF. Okay. So the nice thing is that we've already seen examples of this. These guys here, those are the parallel classes out of a resolvable Steiner system, one that we've been seeing all day. This is the one that we used to build the Steiner ETF we were playing with. It turns out they're not actually compatible. You actually need to add an empty matrix to make them strictly compatible. But then what you can do is just tensor all of them with the rows of a 4x4 Hadamard. And the resulting thing is the 6x16 ETF that we've been looking at all day. That's that Steiner ETF. In fact, anytime you have a resolvable Steiner system, you can build an ETF this way by taking the parallel classes out of it and building your orthogonal, building your compatible orthobiangular tight frame out of those parallel classes plus an empty guy. The group divisible design that we saw, you take the parallel classes out of a group divisible design together with that one extra piece, which is an ETF tensored with an identity. These guys form compatible orthobiangular tight frames. And in fact, that's where we got them. We started with a different set that gave us exactly this ETF, right? Exactly this ETF. In fact, this is a Spence difference set. But the nice thing is that Chen actually constructed a lot more of these. He didn't really view them as this, but essentially what he did was he constructed these extremely nice sets. He was looking for different sets. And on the road to it, he constructed these L nice sets out of a group G. Now we can construct the phi sub j, just like down here, by pulling those rows out of a DFT. It turns out that the way that he constructed them, if you do this correctly, by pulling the complement out for one, and then all the rest just pull those rows out. So pull U1, U2, and U3 out of the DFT over G, or here, just pull the complement of this U0 out. These will always form compatible orthobiangular tight frames. Now, when Chen did it, he was building different sets. And so he then just essentially tensored with the DFT over a group of size L. But that is never a real Hadamard matrix because his L was too big. His L was not of the right size. But there's an observation that we made, which is these guys, it turns out that, you're probably looking at these going like, you've been talking about real ETFs and all of a sudden you've got these complex numbers, but it doesn't matter because the Gram matrices of these guys are real anyway. That L, turns out that it happens that his L is always congruent to 0 mod 4. So there's always a multiple of 4 number of them. So anytime an L by L Hadamard exists, we get a new real ETF from this construction. We take his U sets, build the compatible orthobiangular tight frames, and tensor, and we get a new ETF. One is an eigenvector of the Gram matrix in both ways. You can fix it so that you can get one as an eigenvector of the Gram matrix with eigenvalues 0 or non-zero. And so you get 2 new infinite families of SRGs from this. Anytime there exists a Hadamard that is L by L. So in particular, we wanted to verify that we had actually done something new. So we took the smallest new example, which has 324 things in it, 324 different levels in that COBTF, in that compatible orthobiangular type frame thing. And we know there exists a 324 by 324 real Hadamard. And so we end up with a real ETF that is in about 2 million dimensions and has about 1 million vectors in it. But since the all ones vector is an eigenvector in both ways, we know that we get 2 new SRGs. Well, new, I don't know. So we went to the table, and I don't know if you know this, but that's not on the table because 2 million is a little bit bigger than 1,200. We're still pretty confident that they're new, but we're not 100% confident. But at least they're new examples to us in the ETF literature. We didn't know about the real ETFs. We have a lot more in this vein, but this is just the first on this compatible orthobiangular type frames story. There's more to the story that I'll be talking about in later talks. So if you ever see me talk again, hopefully you'll see new stuff past this. Can I take 2 minutes to tell you one fun story? Okay, there's one more new real new SRG that I found, and it's the craziest story because I just had a wild hair because the 77 by 210 is a weird SRG. There's an SRG on 210 vertices that is a very odd construction. It was constructed via somewhat of a computer search, but it's a difficult construction. But that turns out to be one of the ETFs one of the SRGs, strongly regular graphs, that would arise from an ETF that's 77 by 210. I don't know how to build that ETF myself. But the other one, the other flavor, where the all ones vector is the other type of eigenvector of the Gram matrix, that one was yellow in the table. And I was thinking to myself, I wonder if I can just sign this one and get the other one. And I thought, nah, there's no way you're going to be able to do that. But I thought, let's do it. Let's try it anyway. So I grabbed phi to be that known centered. That means the one that the columns all add up to 0. 77 by 210 ETF. And then what I said was, I really want to find something that's in the row space that is flat. So I want to minimize the infinity norm. And computers don't like to minimize the infinity norm. So I minimized the 4 norm just by gradient descent. So I did that for a while. And it took about 30 seconds until I found it, right? There's a way you can sign that that SRG on 210 vertices. Essentially, there's a way you can do a switching equivalence and get the other one, the one that wasn't known, the one that is 210, 95, 40, 45. The really scary part about this story is that when I run this algorithm again, it takes several hours. It took 20 seconds the first time. The second time it took 3 hours. I don't think that I would have waited 3 hours. So the only reason that we know that this SRG exists is because I got lucky one time. Anyway, I thought that was a fun story. Thank you so much for your attention.
That was a very interesting talk. Are there any questions? Maybe one question I'll start with is there some kind of geometric intuition you would get why you're getting a strongly regular graph from the equiangular time frame? What does it have to do with those?
I can tell you a little bit about the geometric intuition about this. So when the all ones vector is in the row space versus being versus the columns adding to 0. When the columns add to 0, what that's telling you is that your average is 0. Which, so when I think about a generic like ETF, I kind of think about it as having an average of 0, but it really doesn't have to, right? Like, because I can sign the vectors however I want, right? And so that really has the flavor of the angle, right? Because when I'm talking about the graph that comes from it, I'm really thinking about when are the inner products negative and when are they positive, right? And so the fact that it's centered, that the average is 0, really doesn't, it's not too much of a leap to believe the number of negative inner products and the number of positive inner products should be the same no matter which vector you look at, because there's sort of extra symmetry there. Does that make sense?
Okay, so
A similar thing holds for when the all ones vectors in the row space. That's when the vectors are what we call axial. So they have a similar type of symmetry. And so that's what enforces that all of the number of negative inner products from one vector to the others doesn't depend on which vector you pick. And so that gives you the regularity in the graph that I was looking for, that is necessary for the graph to actually be an SRG.
Okay, that's interesting. Thank you. So there's a question in the chat from Max. Yeah.
Other than this last example, do you ever get switching equivalent graphs from the two types of signings? Yes, very frequently. So in fact, it happened early on in the talk. The 6x16 that I showed. I'll show you again. So we did that, and then we express from ETFs, and then we did there. These two, they're switching equivalent. So in fact, anytime you have a balancing a BIBID, a balanced incomplete block design, or a Steiner system, so BIBID with lambda equals 1, that even contains a single parallel class, and such that the resulting ETF is real, you get both types, and they're switching equivalent, right? Because you can, all that I needed here was this parallel class here, this 100101110, that parallel class. That's what I needed to get the all ones vector in the row space. But the Goethals and Seidel construction, they actually only ever gave you the ones where the columns add up to 0, because each of these individual pieces, like these 4 columns, add up to 0. So these two are switching equivalent. And you can always do this with these Steiner ETFs. You can always get them so their columns add up to 0. And we've only ever been able to do it, and it's probably only true that if there's a parallel class, you can get the all ones vector in the row space, and then you can sign to go back and forth. I think your question, I have a question back to you, Maxwell, which is, are you surprised that these two different SRGs are switching equivalent to each other? Okay, good. I'm glad to hear that opinion, because like it's been asked routinely when I talk about this stuff. It's like, you have lots of examples where the two are switching equivalent, and I'm like, yeah, but it's not that surprising because Steiner ETFs do it all the time. The other examples, not as frequently, but still there are lots of other examples where you can just sign to go back and forth. You can switch and go back and forth between these two types. Yeah, right. And essentially, that's what happens, is essentially, if your short fat representation is nice enough, then you can just automatically see, oh yeah, there's a way to do this so that the all ones vector is in the row space. Hey, there's another way to do it so that the all ones vector is in the kernel. Like, and that's why these nice short fat representations, I think, are really nice, because they allow you to see that kind of structure and exploit it almost just visually. Cool. Thanks for the question.